In the last session, we've built a gas turbine model from scratch. And not only did we do that, but we were also able to verify that it can replicate the manufacturer's performance data. Now, that gives us something quite powerful, a simulation that we can use to answer engineering questions. So today we are going to look into a topic that is talked about a lot in power generation industry, and that's hydrogen blending. Sometimes hydrogen gets described as a simple replacement for natural gas, and that's putting in a little bit of hydrogen and then reducing your emissions. Unfortunately, from a thermodynamic and operating perspective, the story is not that straightforward. So in this session, we are going to introduce hydrogen in our fuel gas, crank it up all the way to 20%, while we maintain the total energy input to the system. And that's quite important because that's going to allow us to isolate the changes that are happening because of the hydrogen addition. And while we do that, we are going to be keeping track of some key performance indicators. For example, we'll be looking at the mass flow rate of the hydrogen, we'll be looking at the turbine thermal efficiency, the turbine power output, and we might also look at the flue gas composition to make sure that we can understand and see how the machine responds to these changes that we're putting in with the hydrogen. And before we go into the model, let me ask you a quick question. What do you think will happen if we maintain the system energy input? Basically, we are not putting more energy to the system, we're just changing the hydrogen composition. What do you think will happen to the power output of the turbine? While you're still pondering on that, how about you go grab your coffee, popcorn, and I will see you in HYSYS. All right, the most important step in this whole thing is to first make sure that we've got the hydrogen reaction all set up. And to do that, we go back to the properties, reactions, and remember we've set up the combustion reactions, but we didn't include the hydrogen. So now we're going to add a reaction for hydrogen, conversion reaction, add reaction. Then I'm going to just close this one, click there, and then rename this to hydrogen. That's our hydrogen reaction. Press enter, double click on it, and then we're going to insert the hydrogen. It reacts with oxygen to give us water molecule, and the stoichiometric coefficient will be -2, -1, and +2 of the water molecules, and then we should have a 0 there. That's good. And the base component in this case is hydrogen, and we're looking at the overall reaction, and we are converting 100% of it. Then that will give us fully specified combustion reactions. Then we can come back to the simulation environment. If we didn't do that step, HYSYS was just going to see hydrogen as an inert, so we wouldn't have captured all the thermodynamic properties of that reaction. That is quite important. Now the next step for us to do is to insert the hydrogen stream into the flow sheet, and to do that just go to the model palette, and then I'll insert the material stream. I'll put it just here close to, let me just zoom in here to make the flow sheet a little bit better. I'll zoom in here, double click, and then rename that to hydrogen. And the hydrogen will be coming at room temperature because it will be coming from storage, 25 degrees, and the pressure will be 2330. This is the same pressure as the compressed air and the fuel gas pressure. And at the moment we don't know how much hydrogen we actually need, so we're just going to pick 1 kilogram per hour for now to get the stream to converge, and then we'll work out what the mass flow rate needs to be. And then from a composition perspective, this is clean 100% hydrogen, so the mole fraction is just going to be 1. I'm going to enter 1, okay, and then you can see the whole stream is now fully specified, right? And then we need to blend this hydrogen with the compressed fuel gas. So I'm going to come close to the combustion chamber, right click there, and then break that connection. And once I break the connection, I'm going to insert a mixer and then double click on the mixer, and I'm going to call it the blending station. And from the blending station, our two streams coming in. The first one is the hydrogen stream, then the second one is the compressed fuel gas. And what goes out, we are going to call it the fuel gas blend, a blend of natural gas and hydrogen. And the fuel gas blend goes into the combustion chamber of the turbine. So click on the turbine, and then we're going to insert the fuel gas blend into the turbine, and you can close that. That's all connected up. Let me just configure the streams here just to make it a little bit better. Okay, so far it looks like we've got our geometry all sorted. If I were you, I'll just take a screenshot of this table. It will be our reference point for the comparison of the hydrogen blend versus just natural gas. So these units are incorrect. We should just fix them up for now. Let me just do that while I'm here. It's unitless. Great. Okay. I need to refresh this table. There you go. Now we've added the hydrogen stream, and its flow rate at the moment is just 1 kilogram per hour. You can see the composition of hydrogen is 0.0019 mole fraction, right? We want to get that to be 20%. But before we do the flow rate adjustments, first let's have a dashboard or some sort of an indication to track our key performance indicators. And for that, I'm using the spreadsheet tool. And I'm going to double click on it and then rename it to blend gas performance indicator. And I'll come to the spreadsheet, and then now we're going to ask ourselves that fundamental question. What are we really trying to track here? It's obvious. The first one would be the hydrogen mass flow, and the second one would be the natural gas flow rate, and the fuel gas blend flow rate. 4 would be the fuel gas blend lower heating value. So when I say the fuel gas blend, that's the blended gas, the hydrogen plus natural gas. And then we're also going to track the air compressor power consumption. We're going to also track the turbine gross power produced, and we are also going to check the net electrical power produced, and that will be in megawatts. And then the other variable we are trying to check would be the turbine inlet temperature. We are going to check the carbon dioxide emissions, CO2 emission. We are also going to check hydrogen composition in the blended fuel gas. We ran out of rows. Let me just insert a few more rows there. Just go to edit row, and then you click on 10. You're going to insert a few rows underneath it. So let's go to what, 15, 16 rows. Hydrogen composition. I can close this one here, don't need it now. Hydrogen composition. We're also going to track the flue gas moisture fraction, because of, remember, when we burn hydrogen we produce water rather than carbon dioxide. And the other one that we will be tracking is this is an important one, is the energy input. In the base model we had it in terajoules per day, and then we're going to need the energy input again in megawatts, because that we'll use that to calculate our efficiency, the energy input in megawatts. And then the other one would be the thermal efficiency. I think for now that's okay. If there's anything that we missed, we can always come back and insert those. So this is going to be our, what I call, dashboard. This is where we're going to be running the model and then coming to the spreadsheet and checking how these variables are changing. I could also just put in the reference values for the base model. In the C column, I'm just going to put in what we had in the base model. So what we had before we changed hydrogen stream, which is these values here. I'm going to double click on there. The thermal efficiency was 38.93, and the turbine power produced, the net power produced, was 22.89, and the turbine inlet temperature. This is also important because this is what determines whether we are breaking the turbine or not in terms of the temperature. This temperature was 1121. So you can see the temperature coming out of the combustion chamber. It's 1124. I think that would be in the material limits of what those turbine blades can take. 1124. We don't want to exceed that temperature when we introduce hydrogen, because remember, hydrogen has got a higher adiabatic flame temperature. So we need to be careful not to exceed this temperature. And then the CO2 emissions from our baseline, or here CO2 mass flow rate, is 11,677 kilograms per hour. And what else can we track? We can track, I think that's about, yeah, for now I think that's okay. Now let's get these key performance indicators for the hydrogen case. The hydrogen mass flow will be coming out from this stream here, and that will be in the conditions. The mass flow at the moment is just 1, but that's going to change pretty soon. And then the natural gas flow rate is this one here. That's the stream there. If you remember from the base model, that was 6,211. We calculated that using the heat rate of that turbine that the manufacturer specified. And then the fuel gas blend flow rate, it will be this stream here, the fuel gas blend. Let me just zoom in here. I'm pretty sure some of you will be struggling to see where I'm getting these numbers from. That's the fuel gas blend flow rate, this stream here, that's going to the combustion chamber. It is this there, 6,223. This is the 6,211 plus the 1 kilogram per hour of hydrogen that we just put in. And then we also want the lower heating value of the same stream. This will be coming from the properties. We don't have it there, so we can add that lower heating value. We come to the property coloration controls, the plus button there, and then on the gas drop down you look for the lower heating value on a volume basis, then apply, and that should be included now in the controls. You just click and drop it there. The air compressor power consumption, that would be coming from the air compressor itself. So I'm just going to zoom in a little bit there. That's the air compressor. Double click, go to the performance, and it will bring out this power consumed. That's still 36 megawatts. That hasn't changed, still the same. And the turbine gross power produced. Now we're going to go to the turbine itself and then double click on the turbine or the expander, double click on that, and then we've got the power produced. That's 59.5 megawatts. So the gross power is 59.5 megawatts, but the net electrical power will be the difference of these two, right? So the power that we produce from the turbine will be B6 minus B5, and now I'm going to divide it by 1000 to make it megawatts and change the units to unitless because it's not kilowatts, unitless, and then we've got that in megawatts, okay? And then the turbine inlet temperature, the TIT, will be this temperature here, the temperature coming out from the combustion chamber. Remember we said we need to be careful, this temperature shouldn't exceed the 2. Okay, and then the CO2 emissions, that would be this stream coming out here, the hot flue gas. We're going to track how much carbon dioxide comes out after we've put in the hydrogen. So you come to the compositions, but you can see the basis here, it's a mole fraction, but you can change it. You can come to this here and then change the compositional basis and change it to mass flow. Once you change that to mass flow, you can close it and then come to CO2. You see that? That's our 11,677 kilograms per hour. You click and then drag and drop it here, okay? And the hydrogen composition in the blended fuel gas. The hydrogen composition in this stream here. Okay, we come to composition and then we are interested in the hydrogen. This here, you click, drag it and drop it there. And then we've got also the flue gas moisture content. Moisture content will be like the same stream, this one here. I want to know how much water we are actually producing after the hydrogen combustion. But this is still the mass flow rate. I'm interested in the mole fractions, and then we get the water, which is the moisture, drop it in there, and then lastly we're going to calculate the energy input. Remember, this is also another important part. The energy input should be the same as the baseline, and then in the baseline our energy input from memory was 5.073 terajoules per day. I hope you still remember how to calculate that. That will be the fuel gas blend flow, which is B3, times the lower heating value, which is B4, times 24 divided by 1 million to make it terajoules per day. That doesn't look right. There's that amount, million. Yeah, that's 1 million. So you can see with that 1 kilogram per hour of hydrogen, we are already exceeding the target. The target is supposed to be 5.073, but it's not too much. It's just a heads up. And then let's calculate that energy input again in megawatts, because that's going to help us calculate the efficiency. In megawatts, it's going to be the fuel gas blend flow, which is B3 again, times B4, which is the lower heating value. That will give me megajoules per hour divided by 3,600, and that should give me megawatts. So that's 58.75 megawatts of energy input. These two are very important because this is one of the key performance indicators, if not the key performance indicators, to make sure that we are not using too much or too little of energy once we start introducing the hydrogen. And then the thermal efficiency, it would be the electrical power output, which is B7, divided by B13, the thermal input, B13 times 100. And I'm going to change that to percentage, and that's our efficiency, 38.96. Remember, from the base we had 38.93, right? So looks like it has gone up just a fraction. However, so far we haven't done much with the model. We just need now to adjust the hydrogen mass flow rate until we reach the 20% hydrogen. This is where the fun starts. Let me just zoom in here. Now we're going to use the adjust tool to adjust the mass flow rate of the hydrogen. Just double click on this spanner there to adjust, put it into the flow sheet, double click on it, and then I will rename it to hydrogen adjust. And so what are we adjusting? The adjusted variable is the mass flow rate of the hydrogen stream. The hydrogen stream, and then we are adjusting the mass flow rate. And then what is the target variable? We are targeting the fuel gas blend stream. We are targeting the mole fraction to be 20%. That's the mole fraction of that hydrogen. We need it to be 20%. The specified target, it's 0.2. And then we go to the parameters. We're going to specify 1 kilogram per hour step change and the maximum of 10,000 iterations. And then I just press enter, and it says not solved, start. And it looks like it has converged. A pro tip I will give you is, once you get the flow sheet to converge, just come here, zoom in to this adjuster tool, and look at this diamond shaped border. If it's black, it means it's good, so there's no issues with the convergence. If it's yellow, it is coming back with a warning. Even though the flow sheet might have converged, the warning means it hasn't really met its objectives 100%. Okay, but in our case, we've got a black border color. That means we are good. So let's just have a look. This stream here, we expect it now to have 20% hydrogen. Now double click on it and then go to the compositions, and we've got 19.98% hydrogen. That's close. I can do that and then open up our dashboard. Double click on here, and we can go back and have a look. Our hydrogen composition is almost 20%, but our energy input is now 5.455 terajoules per day. We said the target here needs to be 5.073. We are not allowed to exceed this energy input. So we need to change the natural gas flow up until we meet this 5.073 terajoules per day. So that's another adjuster that we're going to be using. So same logic, put adjuster, and I'll call this one here the natural gas adjuster. And then what are we controlling there? We're controlling the natural gas flow rate, the standard condition, and we are targeting the energy input, and that energy input is calculated from this sheet here, the blend fuel gas performance indicator. Double click on here, and then we want to target our cell, the B12. We want it to, there you go, and that B12 should be 5.073, right? We got 5.073, and then we go to the parameters. The step change, I'm just going to say 100, and then we're going to have a maximum of 10,000 iterations. Press enter, and then start the solve. This might take some time. No, it didn't, it was quick. And then close it, and then you come back here. Before you do anything drastic, just come back here that and zoom in. Yep, you've got in a black border, so it should have converged properly. Now let's have a look at this dashboard. So we've cranked up our hydrogen to 20%. We've adjusted the natural gas flow rate. It still hasn't met the target that well. Some people will be happy with this. I am not. I will reset this and rerun it again. Maybe I'm going to see, when I say reset, it recalculates, and then now it is almost there. And also reset the hydrogen there at the top. And also reset this one, and then double click and see how it goes. We are pretty much there. I think we're fine. So we've met the energy target of 5.073 terajoules. We have met the hydrogen composition of 20% in the fuel gas. Now let's just talk about what happens. So you can see the thermal efficiency dropped a little bit from 38.93 to 38.84, and the power production is now 22.8 megawatts compared to the baseline of 22.89 megawatts. This is insignificant, right? I mean, we've just been pedantic here. You can see if we crank up the hydrogen to 20%, we don't expect the performance of the turbine to actually drop that much. It's definitely not increasing. It's either staying the same or have a very small drop. What is important is the carbon dioxide, because of the only reason we are doing this is to reduce our emissions. If you remember, our baseline emissions were 11,677 kilograms per hour of CO2 from natural gas combustion. Now we've got 10,853 kilograms being emitted, right? We can calculate that percentage. I think that was about 7%. So we've got C1 minus B9 divided by C9 times 100. So that should be around 7% reduction. There you go. That is percent. So we've got about 7% CO2 reduction. So with the effort that we've put in, 20% hydrogen, only to gain a 7% reduction in CO2. And this is consistent. This is not something that we made up here. This is a natural observation of what hydrogen blending actually does. We go up in the hydrogen purity, so to speak, but we only get about 7% of CO2 emissions. For this study, we are not talking about NOx just yet. Now, NOx emissions are another level of detail that needs to be taken into consideration. But just to show on a high level that enriching your natural gas with hydrogen to up to 20%, you are only going to get about 7% CO2 reduction. If there's any questions or anything that is not clear, let me know in the comments and then we can tackle it. I was going to do a sensitivity analysis, but I think this series has been going on for some time now and we kind of get the gist of it now, right? We know how to build the model, build the HRSG units, and also how to build up the hydrogen in the fuel gas. Depending on what you guys want to see, just let me know in the comments and I will run another video to either look at the heat recovery steam generation system, basically size it up to see how big those heat exchangers are, or we can run the upstream and do the hydrogen production side of the story. So I can run you through how the hydrogen was produced. The hydrogen was not produced from steam methane reforming, it was from electrolysis. So we can run that HYSYS model of how to produce hydrogen using electrolysis. Okay, I hope that makes sense. If it doesn't, let me know in the comments. And I hope you enjoyed your popcorns and your coffee. See you on the other side. Cheers for now.